All right. Hello, everybody. Thanks for having me. So what I'd like to do in the first part of the class is to just try to give you a map of the land of machine learning. I think it's good to get our bearings before we go exploring very deep. And then maybe in the second part we can have some Q&A, which is always fun. Think of it as everything you always wanted to know about machine learning but were afraid to ask. Okay? All right, let me start with a very simple question. Where does knowledge come from? In the past, knowledge came from just three sources. Evolution, that's the knowledge that's encoded in your DNA. Experience, that's the knowledge that's encoded in your neurons. Culture, that's the knowledge that we acquire by, talking with people and reading books and so on. And what is amazing in just the last decade is that a new source of knowledge has appeared on the planet, and that's computers. And notice that the appearance of each of these forms of knowledge acquisition was a major event in the development of life on Earth, right? Evolution is life itself. Experience is what distinguishes, learning from experience is what distinguishes, us mammals from, reptiles and insects. And culture is why humans are who we are and as successful as we are. And I believe that the emergence of knowledge discovered by computers is going to be every bit as momentous, every bit as big of a change as each of the previous three was, and it's just beginning. Notice also that each of these forms of knowledge discovery works orders of magnitude faster than the previous ones, and discovers orders of magnitude more knowledge. And the same thing will be true with computers. With computers, we can discover orders of magnitude more knowledge, orders of magnitude faster than through culture, than through experience, than through evolution. In fact, Yann LeCun, who's a famous machine learning researcher and these days the director of AI research at Facebook, says that most of the knowledge in the world in the future is going to be extracted by machines and will reside in machines. So knowing what this all means, I think, is very important for all of us as professionals and also as individuals and as citizens. So how do computers discover new knowledge? Well, that's what machine learning is all about. And there are 5 main ways. One way is to work in a way, the same way that scientists do. It's by automating the scientific method. We have our existing knowledge, and then we try to fill our gaps in that knowledge, and so on progressively. A very different one, very popular these days, is to emulate the brain. This is what deep learning, which you've probably heard of, is all about. Since the best learning system on Earth is the one inside your skull, what we engineers do when we're far behind is we reverse engineer the competition. So let's reverse engineer the brain and have learning algorithms based on that. Another one is to simulate evolution. Evolution is an amazing learning algorithm, right? It made you and me and all of life on Earth, so maybe we can simulate that on a computer and evolve the things that we want that way. Here's another one, and this is to realize that all knowledge that is acquired from data, which is what we're going to do, is necessarily uncertain. You're never really sure if it's right or wrong. So we need to quantify that uncertainty and then systematically reduce it. The principal way to do that is using probability, and that's what we'll do. And finally, there's reasoning by analogy. This is what we human beings do in our daily lives all the time, and there's a lot of psychological evidence to this, which is when you are faced with a new problem to solve, what you do is you consciously or unconsciously look for parallels with situations that you've been in before, and then you try to extrapolate from the old situation to the new one. And associated with each, so these are the 5 main paradigms of machine learning. And associated with each of them is a school of thought, what you might call a tribe, right? So there are 5 tribes in machine learning. And part of what makes machine learning, very fascinating, in addition to being very important these days, is that each of these tribes has its origins in a different field of science. And so, under the guise of studying machine learning, you can actually study all of these things and have a lot of fun. So the first tribe that we'll meet is the symbolists, and they have their origins in logic and philosophy. Now, each of these tribes also has a master algorithm, a learning algorithm that in principle is capable of discovering all knowledge from data. Every possible piece of knowledge can in principle be discovered from data by one of these algorithms. So the master algorithm of the symbolist is something called inverse deduction, and we will see in just a little bit what that is. The connectionists, so-called because all knowledge in the brain is encoded in the connections between neurons, they of course have their origin in neuroscience. These are the ones who try to reverse engineer the brain, and their master algorithm is backpropagation. Okay. You probably have backpropagation in your pocket right now, doing speech recognition and various other things in your cell phone. Then the evolutionaries, they have their origins in evolutionary biology. Their master algorithm is genetic programming. We'll see what these are as well. The people who are, really focused on uncertainty, they're Bayesians because it's all based on Bayes' theorem. They have their origins in statistics, and their master algorithm is probabilistic inference. And then finally, the analogizers, they actually have their roots in a lot of different fields. They're actually the least cohesive of the 5 tribes, but probably the single most important influence in this type of machine learning is from psychology, because we have learned a lot from how people essentially reason by analogy. And their best-known algorithm is kernel machines, also known as support vector machines. So let's see briefly what they are, right? Just the key ideas and some of the major applications. So let's start with the symbolists. Here are some of the most prominent symbolists in the world. There's Tom Mitchell at Carnegie Mellon, Steve Muggleton in the UK, and Russ Quinlan in Australia. And their master algorithm is inverse deduction. And inverse deduction is based on a really simple and yet very deep insight. And this is the idea that we can view induction as the inverse of deduction. Right? Machine learning is induction. It's going from specific facts to general rules. That is very poorly understood. What is very, very well understood is deduction, which is going from general rules to specific facts. Now, there's a distinguished, history in mathematics of figuring new things out by viewing them as the inverse of the things that we already know. For example, subtraction is the inverse of addition. And, integration is the inverse of differentiation, etc., etc. Addition, for instance, lets you answer questions like, if you add 2 and 2, what do you get? The answer is 4. It's not the deepest thing you'll hear in this class. Subtraction lets you answer the inverse question, which is, what do I need to add to 2 in order to get 4? And the answer, of course, is 2. Now, by analogy with that, deduction lets you answer questions like, if I know that Socrates is human and that humans are mortal, what can I infer from that? And what I can infer from that is that Socrates is mortal too. Now that's a piece of deduction. Induction is answering the inverse question, which is, if I know that Socrates is human, what else do I need to know in order to be able to infer that he's mortal? And the answer or unanswer is, of course, that humans are mortal. And I've just discovered a new general rule, and I can add that rule to my knowledge base, and then in the future I can combine that rule with who knows what other rules to answer questions that are potentially very different from the ones that I saw in the data. The symbolists are actually, of the 5 tribes, the only one that can learn this kind of highly composable knowledge, rules that I can then combine in all sorts of different ways to do different things. Okay, so this is very powerful. And of course, I wrote this in natural language, and computers don't understand natural language. What they use is something like, first-order logic. They use a formal language that is typically logic or some form of it. But the essential idea is the same. And as I said, this is a little bit like automating the scientific method, right? This is what scientists do, right? They look at data, they formulate hypotheses that generalize and explain the data, and then they do experiments to test those hypotheses and then refine them or throw them away and try new ones and so on. And in fact, one of the most exciting applications of this type of learning is precisely to automate science. So for example, the biologist in this picture is not the guy in the lab coat. The guy in the lab coat is actually a machine learning researcher by the name of Ross King. The biologist in the picture is this machine in the back here. This is actually what's doing the biology. Ross doesn't actually know a lot of biology, but doesn't need to. So this, the first machine of this kind was called Adam. This is the second one. It's called Eve, right? They were very imaginative with their names. And what Eve does is it starts with some basic knowledge of molecular biology, DNA, proteins, etc., etc. And then it's given something to study or some goal, like for example, study yeast metabolism. And then it looks at more data. It formulates hypotheses using inverse deduction to explain that data. and then it actually designs and carries out the experiments to test the hypothesis. That's actually what this is here. It uses sequencing and microarrays and whatnot to actually test the hypothesis, and keeps on going. So this is a complete scientist in a box. And a couple of years ago, Eve discovered a new malaria drug that is now in the trials. And once you have one robot scientist like this, there's nothing keeping you from making a million. And now, biology can make progress a million times faster, right? These scientists don't get tired, they don't get grumpy, they're not nasty to their grad students, right? So, very exciting. The connectionists, however, look at all of this and say, well, this is a little bit too abstract, too symbolic, too rigid, too clean. Learning in the real world doesn't work that way. Right? Most of the learning that we need to do, like learning to see and learning to, understand language and so on, is very different. And the example that we have of entities in the world that can do that is us, human beings. So if we wouldn't even be trying to do these things if we didn't know that human beings could do them. So let's take inspiration from them. In particular, let's look inside their brains, right? As I said, let's reverse engineer the competition. So the leader of this school is Jeff Hinton. He is a professor. He started out as a psychologist. These days, he's more of a computer scientist. He splits his time between the University of Toronto and Google. We're all getting hired by these companies at a very high rate. So Jeff was no exception. Jeff really believes that the way the brain learns can be encapsulated in a single algorithm. And he's been trying to discover that algorithm for 40 years. So he's tried longer and harder to do this than anybody else. In fact, he tells this story of coming home from work one day very excited and saying to his family, yes, I did it. I figured out how the brain works. And his daughter replied, oh, Dad, not again. So, he's the first one to admit that his quest has had its ups and downs, but it's starting to pay off. In particular, Jeff is one of the co-inventors of backpropagation, which is an algorithm that these days powers just about everything on Earth. Right? If you go to like Google or Microsoft or Facebook or whatnot, there's just backpropagation being used for one thing after another. And two other prominent connectionists are Jan LeCun and Yoshua Benja. So how are we going to do this? Well, what we want to do is build the simplest model that we can that will do our job, right? So we're going to be inspired by the biology, but our goal here is not to do biology, it's just to do machine learning. So what we're going to do is we're going to try to build the simplest model of a neuron that we can, right? So the brain, the nervous system is made of neurons. We're going to build a mathematical model of a neuron, and then we're going to build a big network out of those simple neurons, okay? So let's start with building a model of the neuron, which is in fact the easy part. A neuron is a very interesting kind of cell. In fact, it's a cell like no other. It looks like a miniature tree. So it has a trunk called the axon, and then it branches out, and the branches are called dendrites. And then these branches at the end of one neuron make contact with the roots of other neurons, which confusingly are also called dendrites. And the places where the outgoing and the incoming and the outgoing dendrites make contact is called a synapse. And what happens what happens is that neurons fire these electric discharges down their axons, called action potentials, which sends a bunch of charge from this neuron to the neurons downstream. And the neurons downstream, if enough current accumulates, they themselves will fire. So it's a null or none phenomenon called an action potential. And when two neurons fire together, if this neuron succeeds in making a neuron over here fire, then the strength of a connection between them goes up. Also known as Hebb's rule, or neurons that fire together wire together. And everything you know, everything you've ever learned is contained in the strengths of the connections between your neurons, in the strengths of the synapses. And which is why this whole school of machine learning is called connectionism. Okay? So how can we model this? Well, very simple. So here's the cell body. It does a weighted sum of its inputs. So the inputs could be the outputs of other neurons, or they could just be the retina. They could be pixels, right? So this could be the gray level in some pixel of a cat, of an image of a cat. Okay? And then, of course, each of these inputs has a weight. This weight is the strength of the synapse. So what we do is just the weighted sum of the inputs. And then if that weighted sum exceeds a threshold, then the output is 1, meaning the neuron is firing and it says, yes, I see a cat here. Okay? And by the way, there's at least one theory according to which you actually have neurons to identify specific things in the brain, right? There were these experiments done at UCLA where somebody found a Jennifer Aniston cell and like a Bill Clinton cell. And, and who knows what went on between them. So this is the basic model of a neuron that we're going to use. And this has been known since the 50s. Okay, so this part is not that hard, and we know how to train those weights and so on. But a brain with one neuron can actually do that much. Actually, it's surprising how much it can do, but at the end of the day, right, a brain with one neuron is not, you can't even really call it a brain. So what happens when you have a big network with these days millions or even billions of neurons? Now we have a very sticky problem, which is here's the image of the cat, and the output should be 1 because it is a cat, but it's 0. So this little brain is doing the wrong thing. And now there's this big mass, this big spaghetti of weights, and how do I fix it? Right, this is known as the credit assignment problem. It's a very important problem in machine learning. Maybe it should be called the blame assignment problem because it's really about deciding who to blame when things go wrong. Okay? And for a long time, people had no solution to this problem, and they despaired of the whole connectionist approach to machine learning. But then in the 80s, this backprop algorithm was invented. So what backpropagation does at heart is very, very simple. What it does is it goes to each of the weights in turn and says, if I slightly increase the weight, does my error at the output go down? Let's say that this should have been 1, but it's 0. If I tweak a weight here and it goes from 0 to 0.1, well, that's an improvement, right? We're getting closer to it being 1. So in essence, what backprop is doing is just this for each weight, and then tweaks until we can improve things. Now, of course, if you really had to do this one weight at a time in a network with billions of weights, you'd never be done. And so what backprop is a very clever way of doing this more efficiently. What it actually does is it first does that for the weights on the output layer. That's easy because that's just one neuron like what we already knew before. And then based on the results for this, it goes and figures out how to tweak the weights of the neurons in the previous layer. And then so on all the way back to the beginning. So what it does is it first computes the output. This is the forward pass, and then sees the difference between the real output, the actual output, and the desired one. That's the error signal. And then it keeps propagating the error back through the layers, which is why it's called error backpropagation, or backprop for short. And as I said, these days there's hardly anything that backprop isn't used for. Backprop is used, in the form of deep networks, for example, to choose what search results to show you when you do a search on Google or Bing, or to choose which ads to show you along with those search results. And to do image retrieval, like on Facebook when they tag images with the faces of your friends and whatnot, they're using backprop, etc., etc., etc. Speech recognition, like the Microsoft, the Skype translator. I don't know if you guys have used that. You can speak into it in one language and the person on the other end. Let's say you speak English and you're speaking to someone in China. They hear you speak Chinese, and then in return they speak Chinese, and you hear them speak English in real time. This is powered by backprop. Okay. But the best known deep network is probably still the one that was on the front page of the New York Times a few years ago. It became known as the Google Cat Network. What the Google Cat Network did was watch hours and hours and hours of YouTube videos. So maybe it should be called the Couch Potato Network, because that's what it was. The journalists called it the Cat Network because the single thing that this network was able to recognize best was cats. And the reason for that is that there's more cats on YouTube than anything else because people love to upload videos of their cats. See all the useful things you're learning today? But in addition to recognizing cats, it can recognize dogs and and people and so on. Okay? And at the time, it was the largest network ever built. It had hundreds of millions of weights. These days there's actually much bigger ones. Now the evolutionaries, they look at this and they say, well, sure, with backprop you can tweak the weights of the connections in the brain. Big deal. Where did that brain come from? Right? The brain was created by evolution. And evolution didn't just create the brain, it created all of you and all animals and plants on Earth. Now that's a learning algorithm worth taking inspiration from. Okay? So this was John Holland's idea. He started working on this back in the late 50s, early 60s. And his idea was we know roughly how evolution works. So what we're going to do is we're going to simulate evolution on a computer. Except that instead of evolving animals and plants, we're going to evolve programs, electronic circuits, or whatever is that we want to have. Okay? And then two other prominent evolutionaries are John Koza and Hod Lipson. So John Holland called what he did genetic algorithms because they're algorithms inspired by genetics. And here's how a genetic algorithm works. At each point of the algorithm running, you have a population of individuals, just as in nature. And each individual is represented by a genome. In our case, the genome is a bunch of base pairs. In the case of computer programs, the genome can so there's 4 values, possible values at each position. But in our case, we're trying to evolve things like programs. They can just be bits. Right? So what we actually have here is maybe 1,000 bit strings. And in the beginning, they can just be random. Typically, you start out the generic algorithm with a bunch of completely random bit strings. And then what you do is so each of these encodes, some sort of program. Then you execute the program on the task that it's supposed to do. And then you measure how well they're doing. This measure is usually called the fitness value of the program by analogy with evolution. So whoever does even slightly better at the task will get a higher fitness value. And then the individuals with the highest fitness get to reproduce. And the way they get to reproduce is literally by taking 2 parents, the mother and the father, and taking the genome of one all the way up to a random crossover point and then switching to the genome of the other. And that generates one child, just as in nature. Okay? And you generate a bunch of children this way, and then you also mutate them. Right? So mutations are basically bits being randomly flipped, just like mutation in biology. And then once you're done with that, you have a new population. So this goes on generation by generation. And the thing that's amazing is that you can actually evolve some pretty sophisticated things this way. In fact, the evolutionaries have accumulated a large number of patents from the US Patent Office for inventing devices like radios and amplifiers that actually work better than the ones that were designed by human engineers, although they're typically completely different, right? Because they're not thinking along the same lines that we do. So this is a surprisingly powerful way to learn. Now, John Koza's idea was that if what we want to do is evolve programs, then representing them as bit strings is a little too low level. Right? A program has a lot more structure than a bit string. And you could have a perfectly good program, and then and then you do crossover, you at some random point, and you destroy it. Okay? So maybe a better thing to do is actually to represent the programs as trees, because a program is really a tree of subroutine calls, subroutine, sub-subroutine, all the way down to simple things like additions and multiplications and whatnot. So, for example, if you had these 2 trees and you pick this crossover point, right, and so what you do is at the crossover point, you take the subtrees and you swap them, okay? So after crossover, you would have one tree that is all the white nodes and another tree that is all the black nodes. And the tree with the white nodes is actually one of Kepler's laws. It's the law that gives the average duration of a planet's year as a function of its average distance from the sun. And this is something that a genetic algorithm can very easily learn. But it can also learn much, much more interesting things, like, for example, how to control a team of robot soccer players. So that was actually, I think that project was here at Berkeley, where they actually did that. And these days, the evolutionaries are having a lot of fun evolving not just programs or even electronic circuits anymore, but actual real hardware robots. This mechanical spider is actually a real spider from Hod Lipson's lab at Cornell. It actually crawls around and survives getting maimed and whatnot. And the way they do this is they start out with the robots in simulation. Once the simulated robots are doing well enough, they actually get 3D printed, and they come out into the real world. And then the spiders start to crawl, the dragonflies start to fly. They also have these robotic dragonflies that were evolved and a bunch of strange monsters. And whichever ones crawl fastest or farthest or whatever the fitness function is, they get to program the 3D printer to produce the next generation of robots. Okay? So this is both exciting and maybe a little scary. If Terminator ever comes to pass, then maybe this is how it'll happen. I mean, of course, these little spiders are not nowhere near ready to take over the world, but but they've come a long way from the random soup of parts that they started out as. The connectionists and the evolutionaries, they're very different at some level, but they also have something very important in common, which is they both take inspiration from biology, which maybe is not a bad idea. But actually, most machine learning researchers actually, they're a little skeptical about that. Their view is, well, biology, who knows? Biology is random. Just because something is inspired by biology doesn't mean it's good. And we want to do the best machine learning we can. So what we actually should do is figure out from first principles how to do machine learning optimally, and then derive our algorithms from that. And the Bayesians are probably the biggest exponents of that way of thinking, and to them, the fundamental principle on which all learning must be based is Bayes' theorem, which is why they're called Bayesians. Okay? In fact, the Bayesians believe that any learning algorithm that is not consistent with Bayes' theorem must be wrong. They're actually known as the most fanatical of all the machine learning tribes. And they have to be, because for 200 years in statistics they were a persecuted minority, so they had to get very hardcore to survive, and and it's a good thing they did, because they have a lot to contribute. And these days they're very much on the rise. So within computer science and AI, probably the best known Bayesian is Huda Pearl. He won the Turing Award, the Nobel Prize of Machine Learning, a few years ago for inventing something called Bayesian networks, which is a way to model the interactions among a very large number of variables very efficiently. And two other famous Bayesians are David Heckerman and Mike Jordan, right here at Berkeley. So what is Bayes' theorem? Bayes' theorem is, and you're probably familiar with, I assume that, how many people here are familiar with Bayes' theorem? Okay, so all right, so this is going to be just a very slight review and redirection of what you already know, right? So Bayes' theorem is something so simple, right, that you'll usually know like in week 1 or 2 of Stats 101, right? It barely merits being called a theorem, except that it's so important, okay? How do we use it in machine learning? And by the way, Bayesians love Bayes' theorem so much that one Bayesian learning startup even had a big neon sign of Bayes' theorem made and hung outside their office for the whole city to see. I think this was in London, right? So they had like a big neon sign of Bayes' theorem. And they also go lay flowers on Thomas Bayes' grave and whatnot. I'm not kidding. This is how religious they are. So how does Bayes' theorem work? Well, here's the idea. I have a bunch of data, a bunch of evidence from the world that I want to explain, right? And the first thing I need to do is decide what is the space, what is the set of hypotheses that that are candidates for explaining the world, and then for making predictions, of course. And the first thing that we do is going to decide a priori how much we believe in each hypothesis. Okay? Before you see any evidence, just based on your general knowledge of the world, how much do you believe in each hypothesis? What is your estimate of the probability that that hypothesis is true? Okay? This is called the prior probability, or prior for short. And this is actually part of what makes Bayesianism so controversial, is that most statisticians and most scientists go like, oh, well, you can't just make up numbers like that and then pretend that they mean something. And the Bayesians say, actually, yes, we can. And a little bit more on this shortly. So that's how much you believe in the hypothesis before you see the evidence, but then, of course, you start seeing evidence. And the idea is that as you see evidence, hypotheses that are consistent with the evidence become more likely, and hypotheses that are inconsistent with the evidence become less likely. If your hypothesis says that what you're seeing is very likely, then what you're seeing makes the hypothesis very likely, right? And this is measured by the likelihood, which is the probability of the evidence given the hypothesis viewed as a function of the hypothesis. And this is something that frequentist statisticians also use, okay? And now if you multiply the two together, the prior and the likelihood, you get the posterior, which is how much you believe in the hypothesis after you see the evidence. And hopefully what will happen is that as I see more and more evidence, then some hypotheses will clearly come out as being the good ones, maybe even just one, whereas most of them become very unlikely. Okay? And the Bayesians look at the frequentists and say, well, see, we got your likelihood here. What you're really doing is just assuming that the prior is uniform. But why should it be uniform? It could be other things. Okay? So the Bayesians' answer to the frequentists is that, like, you guys are making assumptions as well. We're just making them explicit and actually allowing you to make a wider set of assumptions than you otherwise could. Okay? And then you also need to divide by the marginal, which is just the sum of this over overall hypothesis. It's not that important for us. It's in order to ensure that the probabilities sum up to 1. Okay? So this is Bayesian learning in a nutshell. What makes it hard, however, is that when you have a very large hypothesis space, like for example the space of all Bayesian networks, there's far more hypotheses than you could possibly do this exhaustively with. And then you have this probabilistic inference problem, which is very intractable, but the Bayesians have come up with like all sorts of very clever algorithms to do this, like Markov chain Monte Carlo, belief propagation, variational approximations, and so on. So Bayesian learning is used for all sorts of things. In particular, there's a good chance that your first self-driving car will have a Bayesian network somewhere in there as part of its brain, or maybe even as most of its brain. One application of Bayesian learning that we are all familiar with and grateful for is spam filtering. So this was David Heckerman's idea, was to look at spam filtering as a machine learning problem, and in particular solve it with a Bayesian algorithm. So what we're trying to do here is very simple, is we're just trying to decide between two hypotheses. One hypothesis is this email is spam, and the other hypothesis is this email is not spam, also known as ham. So you're trying to decide between spam and ham. Okay? And now the evidence is the contents of the email. So for example, if the email contains the word free in all capitals, that makes it more likely to be spam. And if that's followed by the word Viagra, that makes it even more likely to be spam. Okay? And then if that's followed by 4 exclamation marks, these are all real examples, by the way, that makes it almost certain to be spam. Okay? On the other hand, if it contains the name of your best friend on the signature line, that makes it more likely to be ham. Okay? And these days, people have tried all sorts of machine learning algorithms for spam filtering, as you can imagine. But the first ones, and still some of the best ones, and probably most of them, it's hard to say because the companies don't just publicize it, are still based on Bayesian learning. Okay, finally, let's look at the analogizers. So the idea of the analogizers is that learning is really reasoning by analogy. And I have a new problem, I look at similar previous problems and do my inferences based on that. Okay? And the first analogy-based learning algorithm was something called nearest neighbor. It's an incredibly simple algorithm, and we'll see what it is shortly. You could even say that the appearance of nearest neighbor back in the 50s really marks the beginning of machine learning, because it was the first algorithm that had no limit to how much it could learn. If you gave it more data, it could always keep on learning more, as opposed to the standard statistical algorithms that existed before that made these very narrow assumptions like, distributions are Gaussian and so on and so forth, and therefore could only use so much data. Okay? But for a long time, people were very suspicious of nearest neighbor, and then Peter Hart actually saw that no, nearest neighbor, it works. If you give it enough data, it'll converge to the right answer, which was quite a revelation, and then led nearest neighbor to really take off. The more sophisticated type learning of this type is something called support vector machines, or kernel machines, which you may have heard of, and Vladimir Vapnik was its inventor. Before deep learning took over in the last 5-10 years, the biggest thing in machine learning was kernel machines. And another famous analogizer is Douglas Hofstadter, the author of Gödel Escherbach. He actually really believes that it's all just analogy. His most recent book is actually 500 pages arguing that learning, reasoning, all of cognition is really just analogy. So he really believes that analogy is the master algorithm. And he's actually, in fact, the one who coined the term analogizer. So how does this type of learning work? So let me introduce the nearest neighbor algorithm by the way of a very simple puzzle. So here's the puzzle. I'm going to give you a map of 2 countries, Pozistan and Nagaland. The cities in Pozistan I'm going to mark with plus signs, and the cities in Nagaland I'm going to mark with minus signs. Okay? And now my question to you is, tell me where the border between the 2 countries is. Now you can't answer that question exactly, right, because the cities don't exactly determine the border, but you can actually, make a pretty good guess. Okay? We can actually do this reasonably well. And nearest neighbor is a way to do this. The heuristic that nearest neighbor uses is that I'm going to decide that a point on the map belongs to Pozistan if it's closer to a positive city than to any negative one. That's why it's called the nearest neighbor algorithm, because the class of a point is determined by the class of its nearest neighbor. So for example, if you're doing medical diagnosis using this method, right, you don't actually need to know any medicine at all. All you have to do is have a good, database of patients. A new patient comes into your office, you need to diagnose her, you find the patient with the most similar symptoms in your database, and you predict the same diagnosis. Okay? This looks very dangerous, but it actually does most medical diagnosis better than most doctors. Okay? So I don't know what all those years in med school were for, but I mean, they were for other things. But so, for example, this line here this line is part of the boundary between Pozistan and Legoland, because these are points that are at the same distance, to this city and this city. Okay, and then if you move towards this side, you're closer to this one, so you're positive, and so on. Okay. So this algorithm looks very naive, but it's actually very powerful, even though it's very very easy to understand and to implement and so on. But it has a number of disadvantages. One thing that probably you noticed already is that the frontier that it creates between the two countries is a little bit jagged, right? Real frontiers tend not to have a lot of sharp corners like that. They're probably smoother, at least in some places. So that's one thing. That's probably not quite the right frontier. Another one is the following. Think of what would happen if I just took this city and dropped a nuclear bomb on it, right? The city would disappear from the map, okay? But actually the boundary between Pakistan and Nagaland wouldn't change at all. If you think of the points that are closer to a city than to any other as its metro area, right? What happens is that if this city disappeared, its metro area would be absorbed by the metro areas of these three cities that are also positive. As a result of which the frontier wouldn't change at all. And now on this simple example, throwing away the unnecessary points wouldn't make that much difference. But if you have a data set with millions of examples, you're probably wasting a lot of memory, number one, and then a lot of time comparing with examples that don't really need to be there. What you would really like to do is to remember only the examples that are necessary to fix the frontier where it should be. Also known as the support vectors. Vectors because the examples are usually vectors of attributes, numeric or categorical or both, and support vectors because they're the ones that support the frontier. And this is exactly what support vector machines or kernel machines do. They figure out which ones are the important vectors and they get rid of the others. And they also, into the bargain, tend to create a much smoother frontier. And the way they do this is by a very simple but very insightful idea, which is the following. If I give you these 5 points, right, there's an infinity of different lines that could separate the positives from the negatives, okay? And usually, for example, in neural networks, we just pick whichever one happened to be picked by the random initialization and the learning algorithm. Vapnik's idea is a little more subtle. It's to say, like, they are not all equally good. Which ones are better? Well, think for a moment of these cities as being landmines, okay? Think of this as the DMZ in Korea, right? So this is South Korea, this is North Korea. And your goal, your mission, should you choose to accept it, is to walk across the DMZ, okay, without stepping on any landmines, right? You don't want to die, okay? So if this is what you have to do, what would be your path, right? You could go, your path could be like this, but you wouldn't do that, right? You don't want to step anywhere close to the landmines. You want to stay as far away from them as possible. You want to maximize your margin of safety. So this is actually what support vector machines do, is they maximize the margin. The margin is the distance of the frontier to the nearest example. So what we're going to do is we're going to draw the frontier that goes that while separating the positives from the negatives, passes as far away as possible from all of them. Okay? And when you do this, it turns out you generalize much better and more robustly than if you just had any old random line, because here, there's still a pretty good chance that the next point here is positive. Right? On the other hand, if you go over here, well, you're probably going to, you might be missing a negative example. So the best place to put it is, as far away from both of them as possible. Okay? So this is what support vector machines do. And analogy-based learning is one of the most researched types of learning, not just within machine learning, but in many different fields. And it's been used for just about everything, but probably these days the most widespread and maybe the most important application of this type of learning, and certainly one that we're all familiar with, is what are called recommender systems. So these are the systems that every e-commerce site worth its salt has, that recommend new products for you to buy based on the ones that you've bought before. Okay? New music, new movies, new books, etc., etc. Okay? And these are extremely important. So, for example, Netflix's recommender system is responsible for 75% of the movies that people watch on Netflix. And Amazon's recommender system is reportedly responsible for a third of its sales. Okay? So this little piece of machine learning makes a huge difference. And of course, the way to do this these days people use all sorts of machine learning for this, as for all the other things, but the first way that this was done was with analogy-based learning. And in particular, the insight that people had was, if I want to predict, what movies you would like to see, the obvious thing to do is to try to do it based on the properties of the movies. Do you like romantic movies or action movies or foreign movies, or do you like this director or that actor? But that tends to not work very well because, taste is a subtle thing. The insight was to say, no, what I'm going to do is I'm going to look for people with similar tastes to yours. That's the analogy. It's between you and your near neighbors in taste space, if you will. So, for example, if there's someone, could be, in New Zealand, across the world, who tends to give 5 stars when you give 5 stars and 1 star when you give 1 star and so on, they have similar tastes to you. Or you can measure, the distance between, using the Pearson correlation coefficient was the first thing that people used. And then what I do is, if a bunch of people, if you're near neighbors, typically not just one, but say 10 or 20, if your 20 nearest neighbors all like some movie that has come out that you haven't seen, then maybe this is a sign that you will like that movie as well. Okay? This is the basic principle on which these types of recommender systems work, and it works surprisingly well. Okay, so to summarize, we've met the 5 types of machine learning. We've seen that each one of them has a problem that it solves better than all the others. And it has a master algorithm that solves that problem and can in principle be applied to any data to learn anything. So the symbolists can learn composable knowledge. None of the others can do this. And the way they learn that knowledge is with inverse deduction. The connectionists have a solution to the credit assignment problem, and the solution is backpropagation. The evolutionaries can discover structure, right? The connectionists can only learn parameters, they can tweak the weights, but the structure of the model or the program they can't discover. The evolutionists can, using genetic programming. The problem that the Bayesians are obsessed with is uncertainty. All knowledge is uncertain. The world is full of noise and ambiguity and whatnot. And the way they deal with this problem is using probabilistic inference, based on Bayes' theorem. And the analogizers can reason by similarity. And in particular, they can generalize much farther and from many fewer examples than the others can. If I give you just one positive and one negative example, all these guys are going to be completely stumped. Nearest neighbor will just draw a straight line equidistant between them and say, well, there's the boundary. And it can even do more amazing things, like, for example, think of the analogy between the atom and the solar system that led Niels Bohr to the first theory of quantum mechanics. Right? They had just discovered that the atom was hollow, was mostly empty space, and Niels Bohr's idea was, okay, an atom is like a miniature solar system with the electrons as the planets and the nucleus as the sun. Right? This is an amazingly powerful thing to do. A lot of the greatest discoveries in science come from this type of reasoning. The analogizers can do this, right? They're actually taking knowledge from one domain and applying it in a completely different domain, right? They're going from, the solar system to the atom. Again, none of these would have any idea what to do with that. Okay? So this is very powerful, and only analogizers can do that. The most widely used analogy-based algorithm is kernel machines, but there's fancier ones like something called structure mapping and so on. Now, the more optimistic members of each of these tribes think that their algorithm will solve all problems. Okay? So decade by decade, one school or another of machine learning tends to be on the rise. So for example, right now, connectionists dominate, but 10 years ago, it was the analogizers, and 20 years before that, it was the Bayesians. And 30 years before that, it was the connectionists. Right? Connectionism, these days it's under the name of deep learning, but it's on its 3rd comeback. The first heyday was in the 50s, then they died for 20 years. They had another heyday in the 80s, and now they're having their 3rd heyday. So, If you extrapolate from that, one of these guys is going to dominate the next decade, and if you can predict which one it will be, you could have a very valuable startup on your hands. So each of these solves, one of these problems. But the thing to realize is that all 5 problems are real. So if you really want to attack the hard learning problems, the one that actually have all these features, no single one of these algorithms is enough. You actually need an algorithm that combines the properties of all of them. You need something like a grand unified theory of machine learning. In the same way that the physicists have the standard model that unifies all the forces, minus gravity, but they're trying to get to that. And biologists have the central dogma and so on. Okay? So what we'd really like to have is a single algorithm that solves all 5, and that truly would be the master algorithm. So how can we do that? Well, this is something that a bunch of us have been working on for a while, and we've made a lot of progress. Actually, we're pretty much there at this point. How do we do this? It seems very hard because these algorithms all look so different, right? How could you possibly unify them all? And in fact, some people have said that this is an impossible goal. It turns out to be a lot easier than it seems at first sight if you realize that despite their variety, all these algorithms at heart all have the same structure. In fact, all machine learning algorithms boil down to just 3 elements. Well, whenever you see a new machine learning algorithm, the first thing you should ask yourself is, what's the representation, what's the evaluation, and what's the optimization? So let's look at each of these in turn and see how we can unify them. So the first element is representation. This is the choice of language in which you're going to represent the knowledge that you acquire. So for example, if you're trying to write a program, this could be Java or Python or whatever. Okay? In machine learning, we tend to use more abstract languages, like for example, first order logic. Okay? Pretty much everything in computer science can be easily expressed in first order logics. So that's one possible representation to use, and that's what the symbolists use. But the problem with logic is that it can't handle uncertainty, right? Logic is black and white. Things are either true or false. It can't handle shades of gray. So it's not really good for most real-world problems. Bayesians, however, have a handle on uncertainty. And they do have a very general representation for that, also known as graphical models, because you represent your models as graphs where the variables are nodes, and the edges between the nodes represent interactions. So one type of graphical model is Bayesian networks, which I already alluded to. Another one is Markov networks, which these days is increasingly the one that's most widely used. So if we can unify graphical models and first order logic, we actually have a representation that is good for just about everything. And we have indeed been able to do that. We've developed a number of probabilistic logics that combine the best of logic and probability. In particular, the most widely used is something called Markov logic networks, which, as the name implies, is a combination of logic and Markov networks. And the way this works is actually quite simple. Markov logic is really just logic. So you write the same formulas in logic as before, except that now you're going to give a weight to each formula. So if a formula is something that you really believe in, a very strong regularity that you believe has no exceptions, then you give it a high weight. In the limit, if you give it an infinite weight, then this becomes logic. And the world is a state of the world is more likely if more high weight formulas are true. Right? So the more formulas are true and the higher their weight, the more likely the world is. Okay? So the sum of the weights of the true formulas exponentiated and normalized is a log linear model or exponential family model. People know it by different names, but it's something that we understand very well. Okay? So the formulas with their weights induce a distribution over states. Okay? So that's the representation, very powerful. But now, how do we learn in this representation? Well, the next thing is evaluation. Evaluation is a measure that tells you which candidate programs or models are better and which ones are worse. Okay? So, for example, the evolutionaries had fitness functions. How do we unify the different evaluation measures that people use? Actually, that part is easy, because the posterior probabilities that Bayesians use already have all the things that people generally use as special cases. Okay? More generally, however, what we should do is not actually have a predefined evaluation measure, but a true master algorithm, what it should actually do is take any objective function that you, the user, want to give it. Right? There are a lot of evaluation functions that are convenient for us to use in research, but in the real world, what should happen is if you are a company, you should be doing the learning that maximizes your NPV or ROI, or for example, the click-through rate on the ads, whatever the company really wants to maximize. Or if you're an individual consumer, it should probably maximize some measure of your happiness. Okay, like how, give you the things that you like most, and so on and so forth. So now that we have the representation and evaluation, what remains is to actually find, the model in that representation that maximizes this evaluation measure. Okay, and this is the optimization problem. Okay, it's a problem of searching in that big space of programs or whatever, or knowledge bases, for the one that is actually the best according to this evaluation measure. Okay? And here there's a very natural combination of ideas from the connectionists and the evolutionists. Remember, we're trying to learn a set of formulas. And the formula is a tree. Natural match to genetic programming. Right? We can discover the formulas that hold, more or less, using genetic programming. And then, of course, we also need to learn the weights of the formulas, and here, of course, we have backprop. If you think of the chains of reasoning that are used to explain the data, right, those are trees or graphs, right? In general, they can be graphs, right? But each one of those, you have a formula being applied, and the formula has a weight. You can use backpropagation. You can backpropagate through the chains of reasoning to actually learn the weights. Okay? So we're pretty close to having unified the 5 algorithms and to have a very, very powerful learning algorithm that we're going to be able to do a whole bunch of new stuff with. And some people think that once this is complete, we'll be done. We will have solved machine learning. I actually think that that's a little bit optimistic. I think that on the contrary, once we've succeeded at this, and I think we're pretty close, we will realize that we're actually still very far from solving the machine learning problem, because there are a lot of key ideas that haven't been discovered yet. Okay? And we need those ideas. In fact, one of my goals in writing the book was to hopefully get people who are not machine learning researchers to think about the problem and maybe have ideas that we who are already thinking along these tracks are less likely to have. So, we need your ideas. If you have, any brilliant insights about how to solve this problem, please let me know so I can publish them. So why do this, right? Why not just be happy with the learning algorithms that we already have? Well, the reason is that, as good as they are, and for all the things that they already do in the world and many more, will be done in the next few years, some of the most important, most useful things that we really, really want cannot be done with current machine learning. The current algorithms are just not up to them. So for example, we would all like to have, home robots that do the dishes and make the beds for us and maybe even look after the children. But the problem is that a robot like that, well, first of all, you can't do it without machine learning. Everyone pretty much agrees on that. But the other thing is that, like, if you look at those 5 problems, a home bot in the course of a normal day will run into every one of them multiple times, which means that none of these algorithms is good enough for dealing with them. If we have the master algorithm, on the other hand, we will have what it takes to build the brain of that robot. Here's another one. All of the big IT companies, and there's also a bunch of university projects along these lines, they're trying to create what you might think of as a worldwide brain. Right? If you've heard of Google's knowledge graph or Microsoft Satori, the idea, and Facebook has a similar thing, etc., etc. The idea here is the following. What I really want from the web is not to type in keywords and get back a bunch of pages. That's lame. What I want is to ask, the pages may or may not be relevant, and if they're relevant, then I have to dig, for the information that I want. This is all a lot of pain. What we would really like to be able to do is, just ask questions and, and have the computer tell us the answers. That's what a mature web would look like. Okay? But in order to do that, we need to take the web that's a bunch of hypertext and, a jumble of stuff and turn it into a knowledge base in a language that the computer can reason with. So we need to turn it to something like first-order logic. On the other hand, any knowledge coming from the web is going to be, contradictory, incomplete, full of crap, along with the good stuff. So we need to be able to deal with that uncertainty. which, the Bayesians know how to deal with. So one by one, we are again faced with the fact that in order to solve this problem, we need an algorithm that can handle all those 5 things. Here's perhaps the biggest one, curing cancer. All right, this is, there are thousands and thousands of people, working to cure cancer these days. And why can't we cure cancer with the machine learning algorithms that we have now, right? As I said, machine learning algorithms is actually very good at doing, diagnosis of most diseases, but not for cancer. The problem with cancer is that the reason cancer is hard to cure is that cancer is not one disease. Every patient's cancer is different, has different mutations. The same cancer will mutate as it grows. So the cancer today is not the same as the cancer 6 months ago. The same cancer at the same time may have different mutations in different parts of the tumor. So there is no single drug that you can use to cure cancer like you can do with most diseases. The cure for cancer, or so a lot of researchers believe these days, is not a drug, but a machine learning system that learns to predict for every patient, given given her genome and her medical history and the mutations of the tumor, what is the ideal drug to hit that tumor with without hurting the normal cells. Okay? And if there isn't one, maybe there's a combination that will do it. And if no combination will do it, then maybe we can design a drug from scratch for just that patient. And in fact, this is another application of machine learning these days, is literally designing drugs from scratch. Okay? But in order to do that, we need a level of understanding of molecular biology that we just don't have today. And again, if you try to do that, and a lot of people are trying to do that, you immediately run into all the different problems that I was talking about. So again, you need something like the true master learning algorithm to do that. Okay, one last one. If you look at your life is full of recommender systems. You may not have noticed it, but Facebook has a recommender system to pick which updates to show you. And Twitter has one to pick tweets. And Spotify has one for music, and Netflix has one for movies, etc., etc., etc. But the problem with these recommender systems is that they really only understand a little sliver of you. Right? So Netflix has a system that recommends movies for you based on your movie ratings. Amazon has a bigger one that recommends a greater variety of things, but it's still only based on your clicks and purchases on the Amazon website. So each of these recommended systems doesn't actually know you very well, as a result of which, its recommendations can only be so good. What I would really like to have as a consumer is a recommender system that learns from all the data that I've ever generated. And it builds a really, really good model of me. It knows me better than my best friend. And then what it does is it recommends things for me every day, in the small things and the large ones. Not just, which movie to see next or which, song to listen to, but things like what to major in, what house to buy, even who to marry. Right? I mean, these days, about dating sites, they're all powered by machine learning. Right? They're trying to predict, which two people, are a good match. Their current algorithms are actually not very good. But by the way, as it is, a third of all marriages in America today start on the internet. So the machine learning algorithms are actually the matchmakers, right? They used to be village matchmakers, and now it's machine learning algorithms. Okay? So there are children alive today who wouldn't have been born if not for machine learning. But, right? But think about it, like it's the algorithms that we saw that are actually making those decisions, right? But deciding whether two people are compatible isn't just a matter of their profiles, right? It's like, for example, their taste in music might be relevant, and and their past history, where they've traveled, who knows, okay? So what we'd like to have at the end of the day is a 360-degree recommender that understands you, all around, and that really helps you at every stage of your life. And the big tech companies are in a furious race to win. This is a race, and they want to win. They believe that whoever wins this race is going to dominate, the next era. So, and the way you see this is in things like, Siri and Cortana and, Facebook AM and Google Now, right? And, Amazon has Alexa and whatnot. They are all trying to build a model of you such that they can use it, to interact with you and, know what you like, what you don't like, what they should say, what they shouldn't say. So there's going to be a lot happening in this space. And just to quote Anish Chopra, who used to be CTO of the United States, if we used all our technology resources, we could actually give people personalized recommendations for every step of your life. So this is what we will be able to do once we do have the master algorithm.
Okay, let me stop there. More about all of this in my book, The Master Algorithm. So the idea of this book is to be an introduction to machine learning for a general audience. So there's no math, there's no pseudocoding there, but all the major ideas in machine learning are explained in hopefully not just a useful way, but also an interesting and entertaining one. Thank you.
Let me kick off the question. The question. I know a lot of people who say that if they could go back in time, they would have majored in machine learning. You actually had the opportunity to do that, but you also said that at some point in your life you were concerned that maybe you made a mistake because machine learning kind of wasn't as popular at one point as it has now become. What accounted for sort of the doldrums, or the so-called doldrums of machine learning?
So in my personal case, I actually never had any misgivings, right? But that's, maybe I wasn't responding to the environment, right? So I majored in computer science and engineering. That I think was certainly a good call. At the time you couldn't major in machine learning, right? But then I decided that, I just picked up this book in a bookstore that was called Artificial Intelligence. And I was like, what could that book be about? Like artificial and intelligence didn't really go together. So I read the book, right, and the book was quite fascinating. This was like, AI was still in the primitive state. And there was a chapter there about machine learning. And upon reading that chapter, I realized two things. One was that, yes, machine learning is how we're going to solve every problem in the future, not just in AI, but in everything else, right? Like curing cancer, for example. So machine learning is extremely important. At the time, machine learning was a very unimportant part of AI. People believed in knowledge-based systems and encoding rules by hand and whatnot. But I immediately decided that machine learning is one day. I used to tell people that one day machine learning is going to take over the world, right? And that sounded ridiculous then, but today it's kind of happening. And the way it's happening is pretty mind-boggling. But the other side of it was that it was in such a primitive state, right? Like they didn't know what the heck they were doing, right? So you look at a field with high potential impact that's in a primitive state, that's what you want to get a PhD in. Not physics or math, because those fields are already very far along, there have been Einsteins and Newtons, right? And in machine learning, we're still waiting for Newton, right? We're kind of in the Galileo stage. So I decided to get a PhD in machine learning. But at the time, again, machine learning was not a very popular field, and some of my colleagues, my classmates actually dropped out, right? I remember one student of my advisor said this isn't going anywhere. He dropped out, he became like a Boy Scout troop leader or something like that, which maybe he's happy with. But I persevered. And in fact, at the time we actually have people think that machine learning is something that exploded in the last 5 years. It's been exploding continuously for the last 20. I remember the time when I was in grad school and my slightly older colleagues went from having no job offers in the field to being flown around by all these companies that all wanted to have a data mining lab, right? And so that was the first sort of the data mining wave of mining corporate databases. And then came the web and mining the web and e-commerce and personalization. And then came 9/11 and machine learning was a big thing in fighting terrorism. And then came the whole big data meme. And so every time I think this has grown as much as it's going to, it grows some more. So I'm thinking that now, but I could be wrong. Or maybe the hype this time really will not keep up. So we'll see. Mm-hmm. 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 Mm-hmm.
What can actually solve this problem? That's absolutely not so dull, but just combine and learn in a lifetime. What would be the next? How long do you expect it to take? What is the hardware?
Yeah.
Data to actually see this?
Yeah, so good question, right? So I would say that today we have the master algorithm in theory, but we don't have it in practice, right? And in theory, there's no difference between theory and practice, but in practice there is, right? So, ConvNets are actually a good example. The idea of ConvNets comes from neuroscience, comes from the Hubel and Wiesel experiments with cats, and the cat brain, and they won the Nobel Prize for that. 20 years later, a Japanese researcher by the name of Fukushima developed this algorithm called the neocognitron. That was actually the first ConvNet. But it was directly inspired by Hubel and Wiesel, by the architecture of the visual cortex. But the algorithm that they had was basically very hand, design. What Jan LeCun did was actually not invent convnets. What he actually said was, we're going to apply backprop, to this architecture, which is a very weird idea, because backprop is not a realistic model of how the cortex learns. It's actually more like a model maybe of how the cerebellum learns. The cerebellum is the part of your brain that does the motor control. Okay? So I actually think that we're going to look back 10 years from now and go like, what the heck was that? Like the architecture of the cortex with the learning algorithm of the cerebellum, it's like this weird Frankenstein monster. Right? But then, right, and this was in the 90s. It took another 20 years before they actually got into your into your pocket, and then became widely used and so on and so forth, which involved GPUs and more than so on and so forth. So it took not 20 but 50 years to go from the discoveries of Hubel and Weasel to this algorithm being widely used. So we don't want the next thing to take 50 years, right? So we want it to take maybe 5, right? And I think there are several reasons why it will. One of them is that because machine learning is now so economically important, all these companies are pouring resources into it. There's easily 10 times more machine learning research happening in the world today in 1 year than there was in 10 years before. Okay, so by that standard, we're actually making progress 10 times faster, and things will take 5 years instead of 50. Right? The other side of that is that, and this is what to me as a machine learning researcher is extraordinarily exciting, is that today, if you invent a great new machine learning algorithm, 3 months later, everybody will be using it. These companies are in a race, right? You publish your paper on arXiv, if it truly is better, they'll be all over it. So I think if somebody really does invent the master algorithm, it clearly is a big jump over what went before. It'll be widely used very, very quickly, right? In most fields, you have to wait. In medical research, it might be 10 or 20 years before whatever even gets approved. But in machine learning, it could be this afternoon. So this is not to minimize the difficulty in going from a master algorithm that we have in theory right now to one that we have in practice. And the big difference is that it's one thing to do the type of theoretical unification that I sketched out today. It's another thing to have an algorithm that really is efficient and works in practice with reasonable amounts of data and computation. Okay? And in computer science, you haven't solved the problem until you solved it efficiently. And the ideas that we have are still not there in terms of efficiency and industrial strength reliability. But we are making rapid progress towards it. So yeah, invest in my company. I mean, I don't have one, but who knows? Maybe I will. Yeah. I don't know if it has one. Competitive relative to whom? Relative to the machines? Great question, right? This is a very salient question these days, right? I just came from a conference where people were discussing this at great depth. So I think we should distinguish, and I mean, this is the question that's laden with consequences, right, for the future of society and whatnot. I think we need to distinguish between the near term and the far term. I think in the near term, the worries that everybody's jobs are going to get replaced by machines. Oh, this paper that said half of them, but then there are better estimates now. But nobody really knows. I think the thing to realize is the following: there are a lot of jobs that are going to be automated, just as they've been all along. If I was a truck driver, I would be looking for another profession very quickly, because I think a lot of those jobs are going to disappear on fairly short order. Having said that, it's also important to realize that a lot of jobs will not disappear, and a lot of new jobs will appear. Right? People have to remember that 200 years ago, over 90% of Americans worked in agriculture. And then the McCormick Reaper came along and let one, man do the job of 50. And we're not 95% unemployed now. In fact, there's many more. There's just jobs that people didn't even imagine, like web app developer, right? There's millions of people that make a very good living developing web apps. 10, 20 years ago, that job didn't exist. So a lot of new jobs will be created. And also, there's often this, truck driver to programmer fallacy, which is, oh, we can't return all those truck drivers to become programmers. Well, let's not stereotype truck drivers too much. I think many of them could learn to become programmers. But the bigger point is, the economy doesn't work like that, right? What happens is that, let's say tomorrow, all trucks are self-driving, and Amazon has automated all its warehouses, so those 300,000 people lose their jobs, right? Goods become cheaper. As a result, the demand for complementary goods goes up. As a result of which, people have more money in their pockets, so maybe they'll buy bigger houses, and there'll be more jobs for construction workers, and some of those truck drivers will become construction. So you have to picture all of this happening, right? Now, I think for most people in the near term, the important thing to think about is that your job will not disappear, but it will be transformed by AI. Parts of your job are better done or will be better done by machine learning. What you actually want to do is figure out what those are and automate them yourself. The way to keep your job safe from automation is to automate it yourself. Don't let somebody else do it for you. And then you can start to focus on the higher value things that the computers can't do, but you can. Maybe the things that you wished all along you could have been doing and not actually have the time to do. So, you know, AI in this respect is really just a more advanced form of automation. And automation is really like, it's like having a horse, right? If you have a horse, you don't try to outrun the horse, right? You don't say like, what is my competitive advantage relative to the horse? It's like, no, I jump on the horse and I ride much farther and much faster than I could otherwise. This is in the near term. I think in the long term, it is possible that we will get to a point where computers just do everything, computers and robots do everything better than us. Okay? And that would be a very big shift. I think maybe, you know, things tend to work in S-curves, maybe already starting to see things, you know, it's like, look at the ever-decreasing labor force participation rate, right? There's something to worry about there, right? I think there could come a time within the lifetimes of most of us, it won't be in the next 5 or 10 years, where suddenly a lot of jobs disappear very quickly. And eventually there may be none or almost none. And I think what we need for that is to regard that as a good thing, not a bad thing. Is to think of a world where nobody needs to work anymore because we're all independently wealthy, right? You know, these ideas of basic income, I think, in the end, that's what we're going to have, right? Once the unemployment rate reaches 50%, you know, people in a democracy, I guarantee you, they will vote for very generous unemployment benefits or a universal basic income. So I think, you know, this is how things will pan out in the end. But it, of course, will be a very different society at the end of the day from the one that we have right now. And we cannot be complacent. These things will not happen by default, right? I think, you know, we all have our skills that we, you know, make our living based on. We also have our vote. Maybe at the end of the day, our vote is the most important thing. Because your skills might be made obsolete by machines, but as long as we have a vote, we can vote to make these things happen. Because if we don't, whoever is actually on top of these things will, you know, people also talk about, oh, the machines are going to take over. Machines don't take over. The question is like, who is controlling the machines that are taking over? If it's not you, you know, you're the sucker, right? Like, you know, like in poker, right? So, yeah, good question.
You mentioned that again, these ideas of incredible in gravity that had to question some of the basic assumptions. So when you tried to get into science tribe, was there one tribe or one maybe standout that was difficult to bring in because of the questions and basic assumptions around the other four?
Yeah, was there a more recalcitrant one that had to be conquered by force? They all are very recalcitrant. Because they all think that they have, you know, their own master algorithm. I mean, and there's a lot of people working at it. Like, what I painted was, of course, greatly oversimplified. There's people at the boundaries between all of them, right? I think, you know, like to go back to the case of physics, nobody really knows how to unify gravity with the other forces, right? There's string theory, but, you know, string theory is not provable yet. I mean, like, there's no empirical test, right? The empirical test is, you know, what does Ed Witten think, right? That's the empirical test in string theory. But let's set gravity aside for just a moment and realize that even Newton's laws were an amazing step of unification. In Newton's time, people didn't think that an apple falling to the ground and the planets going around the sun were powered by the same laws. They thought that the heavens and the earth were completely different. So that was a fabulous, you know, unification. And then look at Maxwell, right? Electromagnetism, like his laws, are unifying things that people thought were completely different, electricity, magnetism, and light. That was already amazing. And the standard model as it is now unifies those with a strong and weak nuclear force. So if we can get to a comparable point in machine learning, you know, I'm ready to declare victory. Right? Having said, I think they do have a thorny problem on their hands with, you know, combining gravity with the others. I don't think we will have a similar hard problem unifying all the five. I think, again, the big problem is that there's too much that we don't know yet. So, yeah. No, I see a problem with software not being able to keep up with hardware, right? So the rule of thumb in computing is that hardware improves exponentially, software improves linearly, and people don't, right? So human beings are constant, right? The software is progressing linearly. Actually, you know, to make a slightly more serious point, here's something that everybody knows about Moore's law. What most people don't know is that if you look at most, big computing tasks like matrix multiplication or sorting or et cetera, more speed up in the last 50 years has come from better algorithms than has come from better hardware. So the software is actually doing great. Now the problem in AI up until recently was that we didn't have the hardware that could compete with the human brain. The world's greatest supercomputer is the one inside your skull. Right? Your 10 billion neurons and 10 trillion connections, we don't have that. But we are actually now, so it used to be that we couldn't solve AI because we didn't have the means. We're actually now at that boundary point where, if you take one of Google's big data centers and maybe use it the right way, you are, in the ballpark of having something with the capability of the brain. So I think actually now for the first time we can actually work on, building complete AI systems. And now the big question is we don't know how to do that. Yes, Moore's law is kind of, dying out. I mean, the folks at Intel will argue, to the depth that it's not, but it is. C'est la vie. And that, and the free ride will be over. But I think where it stops will be at a place where we have the hardware to do what we want. So the real problem now is figuring out the algorithm. That's where we need your creativity. So don't go into hardware, go into software. Yeah. Yeah. Well, this, we could spend the whole, semester just talking about this. But let me just say a few things. You know how, William Gibson says that the future is already here, it's already very unevenly distributed? Machine learning is an element of such field, and it's extraordinarily unevenly distributed. Okay, so there are some industries and some companies where machine learning is already used extensively. There's others where it's starting to be used, and then there's others that don't know what's about to hit them. Okay? And what is the difference between those industries? Well, one of them is whether, so for example, the first killer app of neural networks was in finance in the 80s. People just back in the 80s neural networks didn't work, they weren't used for anything. Not true. They were used by hedge funds that made a ton of money just using neural networks to predict stock fluctuations and foreign exchange fluctuations and whatnot. Finance is a very natural industry for machine learning to take off on because it has a lot of data, right? And it's a quantitative industry. People are already used to thinking in terms of algorithms and so on and so forth. So there, it took off very naturally. And there's a lot at stake, right? If I can predict the stock market 1% better than random, I will be a billionaire very quickly. And millionaires have been minted like this, like the infamous Bob Mercer. You guys know about Bob Mercer? He was an AI researcher at IBM. They went to this hedge fund called Renaissance. They became billionaires. And he's the guy who bankrolled Trump to the presidency and made Steve Bannon, anyway. Things turn out, in different ways. So finance was a natural industry for machine learning. Another one, of course, is the web and e-commerce, because again, there's already a lot of data in electronic form. And, people already think in these terms. And another important factor that people often don't realize is that you need industries that have margins that are large enough that allow you to invest in machine learning without losing money. Right? In finance and on the web, the margins are large. So they could pour money to machine learning. There's other industries, for example, that machine learning is very good for, like, for example, retail. Right? Walmart was actually pioneering using machine learning. But because the margins there are so razor thin, the amount of investment that they can afford to do is much smaller. So there's all these factors like, like how easy is the data to get, how quantitative, how amenable is the frame of mind of the people in the industry, of the managers, to this type of very quantitative, data-driven decision-making. In some industries, it's not. To how much money do you have to invest in machine learning? So what we're seeing is machine learning gradually percolate to more and more industries and to more and more functions within the same industry. If you look at companies like Amazon and Google, there's like the iconic machine learning applications like the recommender system, right? Everybody knows about the Amazon recommender system. But they use it for, for example, demand forecasting, right? Demand forecasting at Amazon is a hugely important problem, right? They want to know who's going to want how much of what when, and this is a natural problem for machine learning. They have a lot of people working on that. They're so confident that they can do this well, by the way, that they've introduced this thing, experimentally called predictive delivery. Predictive delivery is they send you your Amazon order before you put it in. They're so confident that they know what you're going to order that they put it on the truck, and then and then you get it, and they say, right? I don't think they said this publicly, but they say that, or maybe they have, that if they deliver something to you that you didn't order, you can just keep it. So this is how, so this is just another example, right? So we're going to see more applications of machine learning within each industry, and we're going to see it spread rather to more and more industries. I don't think a priori there's a single function in the world that is not potentially amenable to machine learning. That's actually the part of it, is that it's applicable to just about everything. In fact, I was talking with a VC yesterday from Greylock, and he was asking me a similar question, and I said, what you could do as a VC or as an entrepreneur is go to the BLS, the Bureau of Labor Statistics. They have a list of occupations, right? Like all the occupations in the U.S. There's like, I think, tens of thousands of them. Go to each one of those and think about, like, is machine learning already being applied to it? Is it not being applied? And if so, could it be? And maybe there's a multi-billion-dollar startup right there. So yeah.
Great, thank you
Yeah,
so
thank you.
much for fascinating talk. I recommend everybody buy your book right here. Fantastic. And we've got a little hoodie
thank
for
you.
that you can take back to Washington
Alrighty.
and be the most fashionable guy back in Washington.
And then all the Huskies will murder me, right?
That's right. So thanks again.
Yeah, thank you.
All right.
Yeah.
Fantastic. So we'll be back at 1:30. Okay, 1:30. Okay. Are you going to for lunch?
Yeah.
Okay, great. So those of you do you have your, did you bring your
That what?
data key or your thumb drive or anything?
No, well, I did, but I just downloaded it, so I have it in my pocket. Yeah.
All right, you're going to keep this over there? Yeah. Okay, the sheet is our cinnamon pie. So a bunch of the students will be meeting us for lunch.
Sure.
Yeah. You're going to come too, right? Okay, great. Fantastic. I think, all the topics that you mentioned are ones that we've been talking about. This morning we actually went through the nearest neighbor.
Oh, perfect.
Giving a very sort of rudimentary introduction to all the different algorithms and then talk about applications across all the different industries.
Cool.
So, have you been getting bombarded with from companies?
Oh yeah. No kidding.
How are you able to stay in academia?
It's a choice, right? I mean, some of the things that I get, 90% I don't even reply to, and then 9% maybe, I talk to them on the phone.